Well, welcome back, friends. The Fundamental Theorem of Calculus has a second part. The first part helped us to take derivatives of integral functions. This part is going to help us evaluate definite integrals, and therefore the Fundamental Theorem of Calculus Part 2 is the one that we use more often. And we're going to actually build this one. This is buildable. So let's play this game. Suppose that you have some function f and it's continuous on the closed interval ab. You already know that there's this area function. We're going to call the area function capital G. And capital G is going to be the integral from little a to x of little f of t dt. And we know that this exists. This is the area function. And the area function is that thing that we built in previous lessons whose derivative is little f. Now, let capital F of x be any antiderivative of little f. You're saying, wait a second, this is an antiderivative of little f because the derivative of capital G is little f. And I say, yes, but I also say that there are lots of antiderivatives of little f. So what do we know? We know that capital F of x is the same thing as capital G of x plus some constant. So consider the following, Bill Nye the Science Guy. Consider capital F of b minus capital F of a. Capital F of b minus capital F of a is capital F of b minus capital F of a and the c's are going to cancel. Well, let's think about what this is from a definitional standpoint. This is the integral from a to b of little f of t dt minus the integral from a to a of f of t dt, but we know what this is. This is 0. And so look what we've got. We've got that the integral from a to b of f of t dt is the same as the antiderivative evaluated at b minus the antiderivative evaluated at a. And that is what gets encapsulated in the Fundamental Theorem of Calculus, Part 2. And it says like this: if f is continuous on the closed interval ab, and if capital F is any antiderivative of little f, then the integral from a to b of little f of x dx is capital F evaluated at b minus capital F evaluated at a. And the moral of the story here is that this is a recipe for evaluating definite integrals. If I have some area I'm looking to find, I can find that area by just finding an antiderivative, substitute, substitute, subtract. Like this. Find the area under y equals x squared from x equals 0 to x equals 1. And this is something that we have considered as a class before. And when we considered it as a class before, we actually found all the rectangles and did a Riemann sum, and it was like, wow, that's a lot of work. But here, all we have to do is say, this is the area I want. I want the integral from 0 to 1 of x squared dx. And the Fundamental Theorem, Part 2, tells us that we will come up with some antiderivative for this. And the antiderivative for this would be 1/3 x cubed. And we would evaluate that between 0 and 1. That is to say, we would substitute 0. Nope, let's try that again. We would substitute the 1. We sub in top first. Then we would substitute the 0 and subtract the answers. Done. It's that simple. Done. Okay, so what about this? Find the area under y equals 1 over x squared on 1 to 3. So I've got some function, and there's 1, and there's 3, and this is the area I'm seeking. Again, as a definite integral, it is the integral from 1 to 3 of 1 over x squared dx. So if I had an antiderivative, I would evaluate it between 1 and 3 and be done. That's the recipe. The recipe says I find some antiderivative, write it there, and then sub in 3, sub in 1, and subtract. Well, algebra to the rescue here. This is x to the minus 2. And the antiderivative of x to the minus 2, the power goes up by 1, and then we divide by that new power right there. And so what do? Sub in 3, sub in 1, and subtract the answers. Sub in 3, sub in 1, and subtract the answers. I get 2/3. Okay? Okay. So want to find the area bounded by y equals 4 minus x squared and the x-axis on 0 to 3. No problem. Well, sort of a problem. Because that's 2. And so you actually have 2 areas to worry about. You have this area to worry about, and you have this area to worry about. And I'll tell you why. If you were to just do one integral, if you were to take the integral from 0 to 3 of 4 minus x squared dx, then all of this area would have a positive integral value, but all of this area would have a negative integral value. And so we wouldn't get total area, we'd get net positive area. We don't want that. We want the total area bounded by the parabola and the x-axis. So I don't want to go this way. I actually want to go, sneak in here. I actually want to go this way. If I could throw this into my calculator, and if you're working with an 83 or an 84, it's the FN int, and there are the 4 commands. You've got absolute value of this, comma, x, comma, start, comma, stop. This is always an x. This is always where you start. This is always where you stop. This is the thing you're integrating. If I had access to a graphing calculator, I would totally do it that way. Now, if you're working with one of the fancy new operating systems, you just hit the integral button and boom, it fills in some template for you. But if you're working with a very old school TI-83 or 84, you have to write out the commands like that. This is the kind of thing I'm gunning for. But I can do that by hand. I can find the blue integral and I can add the opposite of the red integral. And I'd have to add the opposite of the red integral because this is going to be a negative integral value, and I want to turn that around positive. So this is a negative number. I subtract a negative number, it turns around positive. So how do I do that? Well, this, I find an antiderivative, evaluate between 0 and 2. And then I find an antiderivative, evaluate between 2 and 3. And I subtract all the answers. So let's see, antiderivative, that's 4x minus 1/3 x cubed. And that same antiderivative is going to work here. So what have I got? I'm going to sub in 2. I'm going to sub in 0 and subtract the answers. And then I've got some big set of parentheses here. Going to sub in 3. Oh gosh, 3 cubed is 27 divided by 3 is 9. Minus what I get when I sub in 2. And what does that turn out to be? It turns out to be 23/3. You can check my arithmetic on that. This is the fundamental theorem part 2 in action. This is what it does. So, one more. So Pete the particle is traveling with a velocity, and his velocity is 4t cubed minus 9t squared on a time interval from 0 to 6. Let's pretend we want his displacement on 0, 6. And his displacement, that's the change in position from 0 to 6. When I ask you for displacement, that is a straight integral of velocity. No need to take into account change in, no need to take into account velocity being positive or velocity being negative, because displacement is a change in position. You want that net change in that case. And so you're going to take an integral from 0 to 6 of 4t cubed minus 9t squared dt. So I need an antiderivative. Antiderivative of 4t cubed is fairly easy. Antiderivative of 9t squared is pretty easy. And if you were to sub, and subtract, you end up with about 648. Now, mind you, if I asked for distance on 0, 6, well, that's a different question, because there are portions of this time interval where this velocity function is negative, and we'd have to flip all those upside down. So if I'm calculator active, then I'm just integrating the absolute value of velocity, which is speed. I'm just going to integrate speed from 0 to 6. And it turns out, because I'm running oh so short on time, that that's 665.086, and you might want to make sure that you can make a calculator spit that thing out. You might want to ask your calculator to find integral values. If you're running an old school calculator, you've got to find the fnint command. It's under the calc menu, and you would finint the function, in this case 4x cubed minus 9x squared, then comma x, it's always comma x, and then comma where you start and comma where you stop. And that is a quick look at the fundamental theorem of calculus. We will deal with this much more when we are together, and I look forward to seeing you then.